Now we're going to talk about a relationship between some confidence intervals and certain hypothesis tests. So confidence intervals give us more information than just a hypothesis test because they focus on the size of an effect and the uncertainty around the estimate, rather than just the size and whether an observed test statistic is significant. So it turns out we can use confidence intervals for testing the following two types of hypothesis tests, thanks directly to the central limit theorem. The first is the hypothesis test about the average in a population. So if my null is that the population average, let's say, is X, and if I'm testing an alternative that it's not equal to X, at a significance level, say A%, then I can actually construct a 100 minus A% confidence interval for the population average using a sample and go and check if this, my hypothesized null value here, is actually in my confidence interval. I fail to reject the null. And if it's not, I can reject the null at A% significance. Let's look at this for our example with the baby data. So suppose here I wanted to test a null hypothesis that the average age of the mothers in the population is 25 and that the random sample average is different just due to chance. My alternative is that the average age of the mothers in the population is not 25. And I'm going to use 5% cutoff for the p-value. So if I look at my 95% confidence level and I go check it here, I can see that 25 is not in this interval. Since 25 is not in this interval, I can reject the null. 25 not in the confidence interval means I can reject the null at the 5% significance level. Now, what if you said, okay, all right, but is that true at an even higher significance level? So let's look at the 99% confidence interval because we know that's going to be wider than our 95. So let's do this one. I'm just running it here. And again, I'm going to still keep my null that the average age of the mothers is 25. And again, I notice, okay, my confidence interval here is a little wider, but not enough to actually include 25. So I can actually still reject the null that the age is 25, now at a 1% significance level. So I can say that this result is highly statistically significant. Now I'm going to contrast this with, let's suppose we had changed our null hypothesis to be that the average age of the mothers in the population was, say, 27. Let's say I had done that. And let's go back to the 5% cutoff. So we're just back to the same question. Now, because 27 is in my confidence interval, it is possible that 27 is the actual population average. It's also possible that 26.8 is, or 26.9, or 27.4. And so that is why we say we fail to reject the null. I don't say that I accept the null or the null is true. I just fail to reject it. It's quite possible that 27 is true, and it's also quite possible that 27 is not. I don't have enough information to reject it. Let's return to the slides. And I'm going to point out this also will work when you're doing hypothesis testing about population proportions, because population proportions can be written as a mean. If you take average a bunch of zeros and ones, it will give you the proportion of ones. So I can set it up the exact same way and again use a confidence interval to test whether or not my null about the proportion is correct. So now let's look at a visual to try to get some more intuition as to why there's this relationship. So I'm going to suppose I'm doing a hypothesis test. My null hypothesis is the population average is some value, let's say 10,000. And my alternative is that it's not equal to 10,000. I'm just going to call it mu sub naught because that's going to look consistent with the picture I'm about to put up. And suppose I'm going to do this at a significance level of A%. All right, well, what I'm going to do is, again, simulate my tests, the distribution of my test statistic under the null. So this is the distribution of, my test statistic would be the sample mean, distribution of the sample mean under the null hypothesis. And altogether, the area here in green, this has to be A over 2, and this has to be A over 2. So let me talk about what that means. When we've been doing our tests, I've always had us create our test statistic. So the test statistic is the sample mean. I've had us do it so we don't have these two tails whenever we're doing a not equal test. So we usually do an absolute value and combine this distribution and just look in one direction. But for the purposes of understanding how hypothesis tests connect to confidence intervals, it's actually useful to keep both tails. And so again, the idea is if I were to see something in my observed test statistic, if it was so extreme that it was out here in one of these green tails, right, where the area, if this was a 5% test, the area of this green tail here would be 2.5%, the area here would be 2.5%. And so I'd be looking for any test statistic that is in one of those green tails to reject my null. Okay, if I get a test statistic that extreme, then the probability of seeing that statistic and something more extreme on either end would be less than 5%. Here is one such test statistic. What I have colored in blue is the equivalent p-value. Again, we didn't learn this using two tails. We combined them all into one tail, but it's the same idea because I'd be looking at the probability of observing this sample mean or something more extreme in either direction. Now, if this were my hypothesis test, well, my conclusion would be to reject the null because it's very unlikely that I would have observed this test statistic in a world where the null were true. How does this relate to confidence intervals? Okay, so now I want you to imagine that instead of doing this work to simulate this test statistic under the null, you instead just start with your observed test statistic and you create a confidence interval for it. My observed test statistic is a sample mean. So a confidence interval for that sample mean is going to be this interval from here to here, right? And it's directly related to the sampling distribution of the sample mean. Okay, so what you'll notice is in this confidence interval, my null hypothesis of 10,000 is not included in this confidence interval. You can see right where it is. It's outside the confidence interval, which would then lead me using the confidence interval alone, it would lead me to reject the null that the population mean is 10,000, at least at using a significance level of 5%. So that is how they're related. And these distributions that we are drawing, these are directly a result of the central limit theorem because we're talking about sampling distribution of a sample mean. That's just to give you some intuition. The big takeaway is when you're testing this type of hypothesis test, it's either true that both of these will be true or both will be false. Either the p-value in the hypothesis test will be smaller than your significance level, and the confidence interval for the sample statistic will exclude the null hypothesis value, in which case you're rejecting the null. Or both of those will be false, in which case you will fail to reject the null. So they're basically two different sides of the same coin, and you can use either to help you make conclusions about a hypothesis test.